Welcome to GE Critical Power's Power Talks. Today we are going to talk about why redundancy is important for systems where the power has to be on. We're going to talk about power module redundancy, what it is, how to implement it, and what it gets you. We'll talk about how power modules are connected together and to your load. We'll look at the controller used to control and monitor the system and see why independent operation is also important. And lastly, we'll look at how remote alarms are best configured so that they fail safe and always alert you of a problem. This is the typical configuration for a high reliability DC power system. AC is converted to DC in what we call a rectifier module and used to directly power the load and to charge the batteries. Because the load is directly connected to the battery, even if the rectifier fails or the AC power fails, the load is still supported by the battery, and there is nothing between the battery and the load to go wrong except mechanical connections. To provide an additional level of protection, we can add additional parallel systems of rectifiers to provide an alternate source of load power and battery charge current in case of a rectifier failure. This is called redundancy of power modules within the power system or charger. Additionally, additional parallel systems can be added to provide the level of redundancy required. If the load requires power of n rectifiers, then redundancy is expressed as n plus 1, n plus 2, etc., allowing for the failure of 1, 2, or more rectifiers, respectively. It is important that rectifiers are connected to the bus through a fail-safe switch, usually a FET, so that failure of a component in the rectifier does not compromise the impedance seen at the bus by the other rectifiers. In a typical redundant power system that we just looked at, there is usually a microprocessor-based system controller. The controller allows the user to control and monitor operation of the system, setting charge voltage, controlling current sharing between modules, and sending data to a remote user. The system should continue to operate in the sense that it will still convert power for the load and batteries, even if the controller ceases to communicate with one or all of the rectifier modules, or even should the controller fail completely. In GE systems, the rectifiers do not need communications with the controller to produce power, so whether communications fail or the controller fails, the rectifiers will still work using the most recently received settings. The current sharing may be slightly less accurate, but otherwise it's power as usual. The controller configuration or settings can be saved, stored, and uploaded to the unit after replacement, minimizing the effort required to bring the system back to exactly the same state as before the failure. Alarms can be sent two ways. The most common and reliable is the alarm contact closure. Alarms can also be sent via internet communications. Contact closures can be open or closed, but the best systems will use a normally closed contact, which opens under alarm conditions. In this way, disconnection of the controller will generate an alert or alarm state. Even if the problem is cut or damaged wires, the remote monitoring location is alerted of a problem. Similarly, a controller alarm can be generated by the controller failing to hold its relay closed for normal operation. We've talked about power module redundancy, what it is, how to implement it, and what it gets you. We've talked about how power modules are connected together and to your load. We've looked at the controller used to control and monitor the system and see why independent operation is also important. And lastly, we looked at how remote alarms are best configured so that they fail safe and always alert you of a problem. Thanks for watching. I hope it's been informative. If you'd like to know more about GE's DC power products and systems, please contact your local GE representative or contact us through our website